Alrighty, folks. Today we are going to shift from talking about electricity to talking about magnetism. And we're going to start off by talking about magnetic force and fields, just like we started talking about electric force. So let's go ahead and get into it. First things first, go ahead and set up your notes. Our essential question is, how does a magnet affect its surroundings? Your guiding questions are, what is magnetic force? How do magnetic poles interact? What does a magnetic field show? And why does a compass point north? Our learning target for today, I can explain how magnetic poles interact. All right, so let's start off with, what is magnetic force? Magnetic force is one of the four fundamental forces of the universe. So those forces include strong nuclear force, weak nuclear force, the force of gravity, and electromagnetic force. Now, magnetism or magnetic force is kind of like the opposite side of the coin of electric force. And you're going to see as we go on how closely related electricity and magnetism are. But here's what you need to know about magnetic force. It is the force, a push or pull, a magnet applies to another magnet, metals like iron and cobalt, or moving electric charges. So the closer that a magnet is to a magnetic object, the stronger its magnetic force is. So if you have a like refrigerator magnet and a paperclip, if they're 30 centimeters apart, they aren't really going to do anything. But if you start getting it closer and closer, at some point that paperclip is going to start moving towards your magnet. And especially if you're really close, like just a centimeter away from that paperclip is just going to fly over to that magnet. So the closer a magnet is to a magnetic object, the stronger the magnetic force is. And what you're seeing here, by the way, you've got a stainless steel ball bearing, and you've placed it into a bunch of putty that has a bunch of tiny magnets mixed into it. And you can see that because of the magnetic force, the putty is being pulled up the stainless steel ball and encompassing it. And that's magnetic force in action, because the magnets are attracted to another magnet and being pulled, or to the ball, the stainless steel ball, and are being pulled. What question does the previous slide answer? All right, so magnetic poles. This is the region where a magnet's force is the strongest. And so all magnets have two magnetic poles, north and south. And these poles are on opposite sides of the magnet. So most commonly when people think about magnets, you're going to probably be thinking about a bar magnet. So that's just a magnet that is just a rectangle. And on either end of that rectangle are going to be your north and south pole. You can also have magnets that look like this that are disc magnets. And the magnetic poles on these magnets are going to be on the opposite sides of the disk, north and south. Now, what we need to know is that like magnetic poles repel one another, and opposite magnetic poles attract one another. So if you have the north sides of two magnets facing each other, they're going to push each other apart. If you have the north and south facing each other, they are going to be attracted to each other and pull together. So what you're seeing here with these magnetic disks is that they're all set up, and when this person puts down this last metal disc or magnet disc, the magnets start flipping and moving. And what you're seeing is magnetic force of the poles in action as the poles rearrange so that they are attracted to each other. So as they start flipping, you see when they are repelled from each other, they flip over so that then their attractive sides come together. So that is magnetic poles. What question does the previous slide answer? All right, so in your packet, if you turn, you will find this diagram, a bar magnet. And so this is why I said a bar magnet. As you can imagine, it's just a rectangle with a north pole on one side and the south pole on the other side. So what we are going to do here is we are going to take what we just learned about magnets, and we're going to start putting some information together. So what we're going to do is we're going to do a diagram in just a moment where you take a compass and you place it near the magnet. Now, here's the thing that you need to know about a compass. A compass is a magnet. The needle in a compass is a magnetic needle. It has a north and south pole. So that means when you place a compass near a magnet, the north pole of the compass is going to point towards the south pole of the magnet. So what you're going to do, and we have a digital demonstration here. You're going to place the compass near the magnet, and you're going to see what direction the red arrow points, and you're going to draw an arrow pointing that direction around the magnet. So you'll then move the compass slightly and do this again, and you will draw at least 20 arrows. So maybe you place the compass here, then you'll draw an arrow here. I know this maybe sounds a little confusing. We'll go to the diagram in just a moment. I'll show you. If you're still confused, there is a video showing how to do this and what your diagram should look like in today's Schoology folder. So feel free to jump over and take a look at that. Alrighty, so here we go. You have our bar magnet, as we just explained, and you have your compass right here. And what we can do, you can see, is we can move the compass around the magnet. So I'm going to start with the compass right here. And when I put the compass right in the middle, you see the red needle of the compass is pointing to the left. So what you would do now is on your diagram, you would draw an arrow in this spot on the diagram pointing to the left. And then I'm going to move it right here. And now the is pointing down and to the left. And so you would draw an arrow pointing down and to the left in this corresponding position. So go ahead and move the compass all around the magnet. I want you to draw at least 20 different arrows showing where the compass points. All right, so go ahead and pause the video and do that on your side. All right, so what you just created is called a magnetic field. And this is the space around a magnet where it applies magnetic force. Now, what you will notice is that the compass reacts most strongly near the poles of the magnet, and that is because that is where the magnetic field is the strongest. And so we actually draw the lines very close together at the pole of the magnetic field, both here and here. And you also see the arrows, they go from the North Pole and go toward the South Pole. And so you actually get these kind of loops, these circles showing the magnetic field. So this means that magnetic fields, so basically you either attract or repel another magnet that enters the magnetic field, and that's going to depend on how the arrows or how the magnetic field in the other magnet is oriented. So we're going to show you some examples. You can actually see magnetic fields, and these are all examples in real life here. So what I'm showing you here is you can actually see the magnetic fields of a bar magnet with metal filings. So this is going to be example A right here, and you can actually see those lines that we talked about, okay? And as you get nearer, there's more iron filings around these parts of the magnet, the poles of the magnet, because the magnetic field is much stronger there. In this magnet right here, this is going to be diagram B here. And you can see that when you place two opposite poles near each other, you have a bunch of iron filings that show up there, and that's because when opposite poles are attracted to each other, and so actually the magnetic field between opposite poles becomes stronger, and that's because the arrows align. And so you can see here in B that you when you line up two opposite poles, the arrows are going to go in the same direction, so they're going to get much stronger. So this is opposite poles. Up here, we have two of the same poles, two north poles facing each other, and you can see there are no iron filings between those two magnets because when you have when you have two of the same poles facing each other, the pole or the magnetic fields repel each other, and so the magnets are repelled and there's no iron filings. That's because the arrows, when you have the two north poles of the fields, they run into each other and they deflect. They aren't going in the same direction, and so they deflect each other, and you can see there is no magnetic force here. So what I want you to do is make sure in your notes you have these A, B, and C magnetic poles all diagrammed in your notes for magnetic fields. What question does the previous slide answer? All right, so we talked about compass earlier, and this is going to be kind of where we're bringing this back because the Earth is actually a giant magnet, and that has to do with the fact that the center of the Earth is is a giant metal ball. And so, what this means is because that the center of the Earth, the core of the Earth, is metallic and it's moving, that the it creates a magnetic field around the planet, and this is called the magnetosphere. It is the area surrounding the Earth that is influenced by the magnetic field. So, why does a compass point north? Well, if you think about it, we just said that the compass, the red arrow, is the north pole of the compass. And so, if we had a compass right now, you would see that that red arrow points what we call north. However, if that red arrow is the north pole of the compass and it is pointing, up towards Canada, what does that tell us about that area up or towards the what we call the north side of the world? That means that's actually the south pole of the world's magnet. So, in reality, what we call north is actually technically the south pole. The north pole is actually the south pole of the Earth's magnetic field. A little bit weird, but you know what? It is what it is. Another thing that's interesting is we have geographic North Pole, or the geographic North Pole, and that's at 90 degrees north, and that's like the very top of the world along which it rotates. However, the magnetic North Pole, because of how the core of the Earth moves, is actually not there. It's actually at 81 degrees north, somewhere up in northern Canada. And so, as a result, there is this disconnect between where the poles or the magnetic poles of the planet are and where the geographical poles are. And this is called magnetic declination, the variation a compass shows between geographic north and magnetic north. So another interesting thing, you can see right here the animation we had at the beginning, and what you see here is the world. And what you're seeing is actually the magnetosphere for the Earth, the magnetic field. And this is solar radiation. And this right here is what you're seeing the importance of the magnetic field, the magnetosphere. Because solar radiation, there's a lot of really dangerous stuff that would actually kill almost everything on the planet. However, we have this magnetosphere that helps deflect a lot of the most dangerous of the solar radiation that comes to the planet. And so that's actually a really important part of what the Earth being magnetic, and one of the most important parts of the Earth being a livable place is its magnetic field. Alrighty, folks, I've got a quiz here, so go ahead and pause the video, go through and try to answer the questions, then come back and check your answer. The push or pull a magnet applies to another magnet, material like iron, or moving charge. Since it's the push or pull, that is the electric force. Or, sorry, the magnetic force, blah. Like magnetic poles are going to repel one another. The area that surrounds a magnet where it can push or pull is its magnetic field. Where is a magnetic field and force the strongest? It's going to be strongest at both poles. If two magnets are placed next to each other, opposite poles facing each other, as shown above, the magnetic field between the poles will be stronger than normal because they are attracted to each other. And the difference between geographic north and magnetic north is called magnetic declination. So if you answered those questions like that, you should have gotten 100%. Alrighty, folks, go ahead and take a moment to self-assess on a scale of 1 to 5. Where are you at when it comes to magnetism with force, field, and poles? All right, folks, so based on how you rated yourself, if you're a 1 or a 2, I want you to watch the magnet tutorial videos that I have in Schoology in today's folder. You'll find a lot of good information that kind of help explain magnets and kind of help maybe with a little bit different explanation to have a clearer understanding. And if you're a 3 to a 5, or once you finish the tutorials and you feel strong, I want you to then finish the magnetic field on your bar magnet, that diagram, and then try to answer questions 1 through 5 on the magnetic poles and fields practice. Those are 1.1, 1.2, 2.1, 2.2, and 2.3. And then on top of that, I would like you to if you are stuck with the magnetic field, check out that video I posted of me making the magnetic field and going through piece by piece, and actually do it with a actual compass. So you'll kind of see how that works. So, all right, folks, have a great day.